company called Xona Partners here in Ottawa. And it's a small management and technology advisory firm. I've known Frank for a long time. We worked together on some fairly esoteric metamaterials products, some beamforming things, and basically, Frank and I have, I think, have a good relationship. Frank's been a speaker for us before on Bitcoin and a variety of very interesting topics. So, and a very engaging speaker. The Zona Partners and Frank's focus is on enabling companies leverage these new technologies. So his insights are very, very, very good. And he's also co-founded a number of companies here in Canada and worked for Ericsson's Redline and Metawave. So with that ado, Frank, can I introduce you to your topic, LEO satellites? They can fly, but can they stick? Over to you, Frank.
Right. Thanks,
Yes,
David.
just before we begin, I've got the recording started. I would ask everybody to mute their microphone, please. We've got 1 or 2 bits of background noise coming on. And with that, please go ahead. Over to you, Frank.
All right. Thanks, Steve. So yeah, thanks everyone. Good evening to you all. So today I will talk about LEO satellites to provide an overview and focus a little bit on basically what the question here is: can they stick? Does it make business sense, or is there a business case really for them? So I will address that in the presentation. Um, So now to start, there is really nothing new about LEO constellations. They have been around. Well, there was a big attempt to build many LEO constellations back in the 1990s. Most of them, actually all of them, went bankrupt. Some of them came back to life and became rather successful, such as Iridium. Orbcomm is there and Global Star as well. But what is really different this time is a number of elements. So there are key differences that's happening related to launch technology. There are differences related to the satellite technology itself and the funding models, and also the business models and the engagement of the cloud players. So there are a number of things that have changed since the 90s. Back in the 90s, things were more related to voice communications. And today what we have is internet and internet connectivity and broadband. And that's really now it's become part of everybody's life. And just think about it. When you want to move, one of the first things that you do is you call for a new internet service, right? Just when you do that with water and electricity and gas and other things. So that is setting new dynamics. And today we have a number of constellations that are being planned. So we'll talk about, I will structure the presentation to highlight some of these differences, to highlight some of the key trends, and then to look at the business case, and then look forward into what kind of key trends that are happening in the industry. So that's how we'll organize it. So in terms of, to basically set context, what LEO satellites are, these are low Earth orbit. So they fly in the range between a few hundred kilometers above the Earth's surface, all the way to about 2,000 kilometers. As you can see here on this, there are so many logos, there are so many new constellations in this circle here that you see. Down below, I put Iridium, Orbcomm, Global Star. These are existing constellations today. The International Space Station, for reference, is at 400 kilometers. But then you have a whole bunch of new constellations being planned. Maybe SpaceX is the most famous of them. They have a satellite constellation that will number in thousands of satellites. But there's also Amazon Kuiper. There's also Telesat, which is a local company here in Ottawa and Canada, that's planning a constellation of LEO satellites. And there's also Kepler, which is a company out of Toronto that has already launched a number of LEO satellites. They have 15, I believe, in orbit now, and they're targeting IoT. So all these constellations that you see here, all these names, there are many differences in these satellite constellations. So they're not all the same. And they have different focus. So for example, if you look at SpaceX and Amazon Kuiper, they're more focusing on the consumer broadband. So their consumer connectivity for wireless access and wireless broadband. There are others, for example, like I had mentioned, Telesat is focusing on data backhaul and transport, and that's completely different business case and market. Others still like Kepler and Clio and Lacuna and Fleet and Swarm, all these guys are focusing on IoT connectivity and machine to machine. And they use different technologies. So not all of them are using the same technology. So for example, some of them are using 3GPP cellular technologies like NB-IoT, while others are using LoRa technologies or others. And therefore you see key differentiation between these constellations. So I will address that. So just to show you like what kind of differences and what we look at to differentiate between them. But now I just want to mention that in terms of the satellite today, of course, it's dominated a lot by the big four, you can say, or some of the big companies are SES, Intelsat, Eutelsat, companies like that, and Telesat, of course, is one of them. These operate in the geosynchronous orbit at close to 36,000 kilometers, so 35,786. And in between the two, you have what we call the medium Earth orbit, or the MEO, and you also have constellations operating in that area, like the GPS system at 20,000 kilometers, or most famous one for broadband and data connectivity and transport is the O3b mPOWER, which is owned actually by SES. And this brings like highlights a point here that many of the geo satellite companies are actually now actively looking into these LEO constellations and looking to see how they can leverage that and whether that is a threat to their business or whether it's complementary. So what we have seen recently in the market is a company like Eutelsat invested $500 million in OneWeb. And you have SES that actually owns O3b, and they're planning to expand that constellation. It's of course in the MEO, but it's also competitive with the LEO constellations. And Intelsat actually had an investment in OneWeb before being washed out when OneWeb declared bankruptcy last year. So, and Telesat, of course, they're building their own LEO. So you see that kind of, there's a competitive threat to these geo operators, but at the same time, many of them are looking to see how they can have a play where they have a geo network and perhaps something in the MEO or LEO and have a hierarchical network, so multiple orbits. So that is another concept that is basically happening today in this industry. Moving forward, I want to give an industry backdrop before I move into the LEO aspect. So just to see what's happening in the satellite space from a business perspective, what we see is that many of the satellite companies, they made their business, especially in the early days, based on broadcast. And they're suffering much like all the terrestrial companies, for example, dealing with cable, with basically the cable cutters, right? So people are moving away from cable into online streaming, and you have competition from Netflix and YouTube and so forth. And that is actually driving down the broadcast revenues, and that is a significant trend that's happening today in the geo satellite industry, that this revenue is increasing. On the other hand, there is higher and higher demand for data services. So demand for data and their revenue from data services is increasing. Now, what's happening on the data side is that there is price erosion. So even though there is greater demand for data, but the price per megabit per second is dropping. And that is basically the kind of context in terms of the business for the satellite companies. And that is leading to a lot of stress in the industry. And what you have seen recently, primarily last year, a whole bunch of bankruptcies that happened. So Intelsat, the biggest geo satellite company, declared bankruptcy. OneWeb, of course, is LEO, but they also declared bankruptcy, and then they got recapitalized, acquired by the British government and the Bharti Group out of India, and they got recapitalized. They're seeking $2 billion. I believe they're close to getting that with the recent investment from Eutelsat. Speedcast, GEE or Global Eagle Entertainment also went bankrupt, and LeoSat actually, which was in the LEO space, exited, and they shelved their plans. So a number of bankruptcies in that market. It's very competitive. I believe Telesat, in their revenues, they were down 8% year over year, I believe, and that's primarily because of the mobility market. So if you think of all the ships and the cruise ships and the aircrafts, all that kind of the mobility market went down, right? So all the satellite companies basically took a hit because of that. All right. I'd like to talk a little bit about the differences between the different orbits, because that will factor into the business case that I will talk about later on. So when we have a geostationary orbit, you only need 3 satellites to basically cover the entire Earth. But when we have low Earth orbit satellites, then you're going to need many of them to cover the Earth, right? You need hundreds or even thousands to cover the Earth. And that is a key difference. Let me try to minimize my, all right. Because the coverage of the low Earth orbit satellite is actually small. So you need many of them. On the other hand, the latency is terrific. So the LEO latency will be on the order of 50 milliseconds. Now, of course, it will vary. It can go down, to 30 milliseconds, but it can also go up to 100 milliseconds. It varies depending on the entire end-to-end, but on average, let's say it's 50 milliseconds. And you compare that to 500 milliseconds for GEO, you see that it's hard to carry voice, for example, on GEO, and you need to do a lot of optimization in terms of your packets, for internet traffic, right? The orbital period for GEO, it's 24 hours. It's stationary. Now on the LEO orbit, these things are circling the Earth every 90 minutes or so, depending on their orbit. But they're basically, what's happening is that they're flying very fast, right? So they will, if you're a user on Earth, you're going to see every about 10 to 15 minutes, you're going to have a new satellite that will cover you. So what that means is that if you have your antenna or your user terminal has to be able to track the satellite. And that tracking mechanism will also factor into the cost and will factor into the type of the equipment that you need in order to carry out communications. So that's how I'm trying to relate the characteristics of these constellations, and eventually to take those down and look at the cost, because that will all factor into the cost of the constellations and the service. In terms of the ground stations, for geostationary, you need few of them because you have very wide coverage of the geo satellites, so you don't need a lot of ground stations. But when you think of LEO, you're going to need to have many ground stations. Now, how many, depending on the business case, depending on which countries you want to go into, and also the capabilities of these satellites. So you can design your satellites in a way that will minimize the ground stations. For example, you can add inter-satellite links. There could be laser, for example, optical links that will link one satellite to another, so you can have a bridge in the sky, and therefore you don't need to go from Earth to satellite back down to Earth, right? You can basically then transport the data or route it from one satellite to another until you reach a satellite. So you can do things like that with the LEO, right? And that in itself will add weight, will add more power requirements, will add cost. So that's how these things will factor into the business case. But essentially, the inter-satellite links are a key differentiation between the different satellite constellations. So that's another part. Now, I mentioned about the user terminal because the LEO satellites are moving fast. Then you need to have fast tracking. About every 8 or 10 or 15 minutes, you're going to have to do a handover between one satellite to another satellite that's coming into the field of view. On the other hand, for the geostationary orbit, your satellite, your user terminal, your antenna is going to be fixed towards the sky, toward a single point. It's not going to change. Always, the MEO is going to be somewhere in between. So in MEO, you don't need to have a fast tracking user terminal. It can be moving slowly. Now, the satellite lifetime is another important one, and it will also impact the business case. So for the GEO, the lifetime is 15 to 20 years. And actually, there are solutions today. Just last year, for example, I believe Northrop Grumman, they basically have a service to extend the life of satellites in the geosynchronous orbit. And I believe Intelsat, for example, has leveraged those services. So they have satellites that they're trying to extend by, let's say, about 5 years. So they go there in order to replenish the power and things like that, right? To enable them to go to basically have a longer life. On the other hand, for the low Earth orbit, the satellites have an average age between 5 to 10 years, depending on how they're designed. And that's because of ionized radiation. So their lifespan is limited. And that means when you're launching a constellation, every 5 to 10 years, you're going to have to deorbit those satellites and you have to launch new ones to replace them. So there is a recurring cost in terms of the satellites because you have to continually replenish your constellation. So imagine if you're a SpaceX and potentially you want to reach a 40,000 satellite constellation, then you're going to need to have a consistent launch capability in order to put those satellites in space. And that is another key point. All right. And then, of course, you have the cost to deploy. So a GEO satellite will cost you around $1 billion, but a constellation for LEO is going to have a capex. I mean, it depends. It can be between let's say 2 billion to 12 billion, but it really depends. Or it can be actually a little less, but it really depends on its size and its function. So there's a wide range in terms of cost. Moving a little bit more. So why do we need LEO? Why do we need to have those constellations? GEO is efficient and GEO is not very complex. And it actually does give you good price. It's on the order of $1 million to 20 million per gigabit per second. And I don't think I mentioned this before, but the new kind of GEO satellites, they're called the high throughput satellites. They basically have multiple beams. So their actually antenna is not necessarily one antenna going to cover the whole of Canada, for example, but it can have certain beams, just like you see here on the right-hand side with the LEO, right? But basically they can have high capacity and you just have to launch one, for example, and to serve that area, right? So they're not complex and they're efficient. On the other hand, the LEO are more complex, but they do have a high cost, $6 to $30 million per gigabit per second. That's our estimate. But they do give you very good latency, right? So latency is a key benefit. And there's also another benefit, and that's portability. And what I mean by portability is that you can use the terrestrial waveforms. You can use LTE or 5G waveforms or NB-IoT. And I'll talk a little bit more about that later. But that is important for different aspects, for aspects of mobility and usability, right? So it now becomes, in a way, you are putting a lot of complexity in the constellation, but you are making it easier for the user, let's say, to access it. Now, the user terminal is still a challenge, but in terms of the use case, it's becoming more friendly. But you do need to have more complexity. For example, you may need to have routing, between these satellites in space, right? So there is complexity that it will add. I wanted to talk a little bit about the launch. So I mentioned basically for the satellite lifespan is short, right? The LEO is 5 to 10 years. And so that's one issue. That's why launch costs becoming very important. But they have been coming down. And that's one key difference between what's happening today and what happened back in the 1990s. Back then, the launch costs were very high. You can see here, they were in the order of $10,000 or more per kilo. Today, we're at perhaps sub $2,000 per kilo. Actually, if you look at what SpaceX is launching is at much lower than that, perhaps at $500 per kilo. But they're a special case because SpaceX and Starlink, they own their own launch vehicle. So that's another key difference, is that companies like Amazon and SpaceX, not only that they're planning these mega constellations, but they also have their own launch vehicles in Blue Origin for Amazon, and of course SpaceX for the Starlink SpaceX program. Another trends that we're seeing in the launch industry is that you have a lot of the national space agencies of China and India are actually becoming very active, and India, I believe, now is number 2 in terms of launching number of satellites into space. India is not expensive, and they have been launching a lot of the smaller type of satellites, and actually that has raised some tension because some companies may not get permission from, let's say, the FCC to launch, and they would go to India to launch and things like that. So India has becoming very active. You have a company like Virgin Galactic, which was the first company to initiate this recent SPAC boom, or the special purpose acquisition company. That's a way of funding companies that now over last year with COVID became very popular. Over the last few months, it died down a bit, but anyway, Virgin Galactic actually is the one that started this whole boom. And then you have you have other companies who have been either around or are relatively new startup, like Astra, which is seeking another SPAC. Relativity, which is a company that I believe Telesat has contracted to launch its satellites together with Blue Origin. You have a company like Rocket Lab, which was in the news over last week. I guess they had lost a rocket recently. So you have a number of startups in that space. So bottom line is, there's high competition, a lot of new entrants, even existing players, and driving down the price of launching satellites into space. All right. I would like to talk a little bit about the satellites themselves, just to show you what they are and what they look like and some of their characteristics. I will pick SpaceX as an example only because they're the most popular constellation, and they're like right now leading in terms of deployment. But it's representative of others. So you have altitude, you have weight, which is around 260 kilo. Interestingly, there was some research done on what it would cost them to launch, and the numbers come between $120,000 to $460,000 per satellite. The throughput is around 20 gigabit per second on average for the downlink. They are on an inclined orbit, so they can only today serve between 57 degrees south to 57 degrees north. So they don't have coverage over the poles, but recently they have applied and they have received permission to deploy in a polar orbit. So they will be able to serve or have some capacity over poles. Now, if I were to compare them to OneWeb, actually I'll do that later, so I'll just save it for later, because OneWeb has a lot of coverage over the poles, right? And not as much in the middle. So, but they're trying to rectify that too. The orbital period is 96 minutes. So these satellites are flying very high at around 7,500 meters per second. The coverage radius of a satellite is 574 kilometers. Actually, if you work out the area, you will get the size of a small country. So let's say the size of a UK, for example, like 250,000 square kilometers. So that's the type of coverage area a satellite would cover. They have 3 uplink beams and 3 downlink, so 7 uplink beams and 3 downlink beams. And the lifetime of the satellite is around 5 years. With the cost, I have seen numbers ranging between 300,000 all the way to $1 million per unit, based on the Morgan Stanley estimate. So today they're number one, as I said. As of last weekend, they had 1,578 satellites in orbit, and they have completed 13 launches. Their next launch is next Wednesday, the 26th, with another 60 satellites. So they launch 60 satellites at a time. Actually, the first slide in the presentation, this is the rocket with this. These are the satellites stacked. So there are 60 of them in one go, and there you see them basically. It reaches certain altitude, it launches them, and then they slowly make their way up into their orbit. While they do that, what you see here, these squares that are shiny on the bottom of the satellite, these are antennas, and they were causing let's say pollution to, like in terms of light reflection, reflecting sunlight and causing pollution for the astronomers who are looking at the stars. So then they had to paint that black. But the idea is that there has been many complaints about those LEO satellites obstructing the view for the astronomers and basically jeopardizing that. So that's another. I'm not going to talk about that, but just want to mention it so that you're aware of it. They do plan around 200 ground stations in the US, but ultimately the number of ground station is unknown, and that really will depend on their business plan. Moving to the user terminal, which is a very important aspect in terms of the cost structure. It is a flat phased array antenna with 1,247 active elements. So you can see here, somebody took it actually apart, and you can see the microstrip antennas and the panel antenna, and on the back side you see it's driven by a number of circuits. So these are all power amplifiers and phase shifters and etc. to feed this antenna. Of course, it will scan the sky and it will rotate over a 50-degree angle. I want to like the service that they're providing today is 100 megabit per second for the downlink and 40 for the uplink. I want to talk a little bit about the power. So it's a 4-watt output power, and it consumes on average 129 watts. So this is not like your mobile phone. This is something that looks like a small cell if you're a telecom person, right? It's relatively high power, not too high, but 4 watts is fairly significant, and that's the power that you need. It operates on the downlink in the 10 gigahertz, 10.7 to so they have a 2000 or 2 gigahertz band, and on the uplink it's from 14 to 14.5. They actually have more bands, but I just listed here a couple. And their modem, they do provide you integrated with Wi-Fi and so forth. Now, in terms of cost, it used to be like in very low volumes when they started. It was in the $3,000 range. Recent reports indicate they're more in the $1,500 range. Now they sell this for $500 US. So essentially they're subsidizing this for around $1,000 per unit. And I was particularly interested to understand the power, right? Because that ultimately is something that impacts the cost. If it's the lower power, of course, the easier it is to achieve low. It's those aspects that add to the cost. So when we do our cost estimates, we like to look at these things. All right. I have here a comparison between 4 constellations, and so there are many numbers here, but I don't think really the numbers are important. Maybe some of the, I'd like to maybe stress what differentiates these constellations. So as I mentioned at the beginning, SpaceX and Kuiper, they're basically focused on the user consumer broadband. And you can see actually that they are planning a large number of satellites. So today, the current plan for SpaceX is 4,400, but they do have applied to deploy 42,000 satellites. Same with Kuiper, around 3,200 satellites. OneWeb and Telesat, you see the numbers there. OneWeb changed their business plan. They were after the consumer market, but then after the bankruptcy, they switched to focus more on the enterprise, similar to Telesat in many ways. You'll see the altitudes, but what I'd like to talk about the inter-satellite links. SpaceX today does not have inter-satellite links. So that means that each satellite, basically you need to have a ground station nearby, basically, in order to carry the traffic. Telesat, on the other hand, they are planning to support inter-satellite links from the start, which means they can save on the number of ground stations. So they don't need to build as many ground stations as a SpaceX today. And OneWeb, they don't have it, but then they said that they will have it. So actually all of them are like, many of them actually, when they started, they didn't have the inter-satellite links, but now they're more gravitating toward their second generation satellites, at least, to feature that, because that would save on the ground stations. You can see the throughputs there. The latencies are fairly similar, frequency bands. I'd like to talk a little bit about the coverage. So SpaceX and Kuiper, they are in inclined orbit. So they are planning to cover, they don't have much coverage in over the poles. But as I said, recently SpaceX applied to have coverage in a polar orbit. So they will be covering the poles. On the other hand, OneWeb, they started with a completely polar orbit, and they had a lot of, which means that they will have a lot of capacity in the North and South Pole, but there is little or less capacity in the middle. That's where the population of the Earth is, right? It's all in the middle. But recently they have changed their, not they changed, but they applied, right, to also launch in an inclined orbit. So I think the key point here is that these things change, like the plans change, and these things continuously are in flux. What's important and what differentiates them is their spectrum rights, how much spectrum they have and the priorities, the antenna capabilities, the throughput and the capacity, the orbital planes, the lifespan of the satellites, the onboard processing and the routing, and the inter-satellite links. That's how we differentiate all these satellite constellations. And again, they're all targeting different applications and use cases, so we need to keep that in mind. Some of the applications, so you have transport or mobile backhaul, which is like what Telesat is going after, like one of the markets that they're going after, not everything. Enterprise connectivity is another one. IoT connectivity is different, and you have different types of constellations, like for sensors and low data rate. That's a different type of constellation. Of course, for verticals, another big market will be the mobility market. Anything that moves, plane, trains, even cars and ships of different types. Government is a big customer of, well, GEO satellites today and LEO in the future as well, and critical communication. So these are the use cases. Now I will go more into the business case. So there is an important concept that I would like to talk about, which is the utilization factor for these satellites. So let's say you have a constellation of, thousands of satellites like SpaceX. Well, the Earth is covered, 71% is water. So 71% of the satellites, essentially, they're covering no people, right? Except maybe ships or airplanes, but essentially no people. The landmass is 29%, and if you don't count Antarctica, it's 25%. And then you have, in terms of where people live on Earth. So how much these satellites are going to be used is a very important metric in order to determine profitability. And today, the Iridium constellation, the satellites are only used 4 to 5%. So when you're launching these LEO satellite constellations and you're spending billions of dollars for them, your utilization rate can be, 4 to 5%, but, we don't know the upper limit. It could be, say, 25%, right? We don't know what the aircraft market and the ship market will add, but it's that kind of a factor that we look at when we do the costing of these constellations. So that is something that I wanted to basically introduce because it's important, and that's a metric that people look at a lot, because in a GEO your utilization is 100%, and in MEO is usually around 25-40%. It depends, right? But it's much higher than LEO. All right. Now I'm building up to the business case. I would like to talk about the demand and the offered capacity. So these LEO satellites, they cover, as I mentioned, like around the size of a country. And I'm talking about more like the mega constellations. Again, it will depend from one constellation to another. But what happens is that, if you have a 20 gigabit per second satellite, and if you, let's say, subscribe to 100 gigabyte plan per month, right? 100 gigabyte per month plan, you can pretty much support around 20,000 users. And if you do your capacity calculation based on the speed on 100 megabit per second, then you probably can support around 3,000 users. So the actual number is going to be somewhere in between 3,000 to 20,000, depending on the service quality and the speed, etc. Now, what happens is that in some areas, right? So think of each one of those circles as being a satellite coverage area. You may get an area where you have very high demand for capacity. You have a lot of people, let's say, in that area, but in other areas you have fewer amount of people. In that case, what happens that you will run out of capacity. So now you need to add capacity. Then how do you add capacity in this case? And you have a couple of options. Either you put more satellites into orbit, And that is not very efficient because the utilization rate is low, as we talked about in the previous slide. Or alternatively, you can also complement that by doing steerable and shapeable antennas in order to move more capacity into this area. And that is a very important feature in those satellites. And actually, if you go back to the O3b constellation, the MEO constellation, when the first generation of that, it did not support that kind of ability to steer the antennas into the capacity hotspots. And that is actually part of its failure. So that is something that has the first generation MEO satellites suffered from, and O3b is launching their second generation, in which case they will address this. And this is another key differentiation between these LEO satellites, is the ability for them to steer capacity to where it is needed. And I just wanted to highlight that because I think it's an important concept. Talk a little bit about the life cycle. The life cycle is well, first you have to, you start, you raise funds, you have to get your spectrum rights, you have to get procure the launch services, you have to sell, you have to pre-sell capacity, you have to go on and market before you launch your satellites, because by the time you launch them, you don't want them to be idle. So after you launch, you will operate them. So your cost actually will be the cost of replenishment if you're a LEO. So you're going to have to continuously bring satellites down and put some others up. But essentially the cost will go down a little, but you still have some cost. And that's the refresh cycle. So that's really, that's really the life cycle of a constellation. So if we model it financially, we get something like this. You first spend a lot of money and you run into debt. And then after a few years, which at least 3 or 4 years, actually, if you look at some of these constellations, they started even, back in 2012 and 13, right? So before launch, they actually spent more than 3 years. But let's say in this scenario, you spend 3 years, it's going to take you another 5 years or so to break even. So for a total of 7, 8, 9 years for you to generate profit. So the gray is actually the revenue. The orange are your costs and expenses. And the green line is your cumulative profit. So you break even, let's say in this scenario, in year 7, because I'm counting from -2 until year 5. Year 0 is your first launch. So what happens is that we've been looking at who could invest in these things and what type of investor. You need to have very patient investors to go into LEO. These can be countries. It can be very special type of PEs. But what recently has been happening is that you have a lot of SPACs, or the special purpose acquisition companies. And I'm not quite sure that this is probably the best model for it, but in any case, that's what's happening on the market. So we shall see about that. But you do need very high capex initially, and you need to have a long time to break even. So you could make money, and these LEO constellations can break even. And the best evidence of that is Iridium. So Iridium is today profitable, and but you do need to be very patient. So that's really the message here. In terms of the cost, there are 4 key elements to the cost in the LEO satellite. So you have the cost of the satellite, you have the launch cost. These 2 costs are relatively predictable, so you can plan for them. But what is less predictable is the ground segment cost and the user terminal cost and the revenue. So these 3 are not as predictable. And of course, the cost of the user terminal is linked directly to the revenue or to the number of subscribers that you're going to get. And that is a big risk element, is that if you're going to build these constellations, will people come? And will you be able to cost reduce the user terminal to low enough cost that you will make, like, the business case will work? And in terms of the ground segment, then you have trade-offs in terms of how much you design and how much extra cost you incur on your satellites in order for you to save on building the ground segment. Now, sometimes the ground segment is related to regulatory issues, so you have no control over that. So I'll go ahead. I think I talked pretty much about this slide. I probably just want to mention that there's the challenge of space debris, which I haven't talked about. I just want to mention that this is a big issue related to the LEO satellites. So, but I just want to leave it at that, just to make you aware of it, that this is something out in the news. But pretty much I talked about all the other elements here. Now I would like to talk about some of the trends, what we see in the market and going forward into the future. So the first trend that we see is the integration of the 5G networks or even 6G when that 6G comes, but it's in discussion, but 5G for now, to integrate that with satellites. And there are different ways in which you can integrate it. You see those in the graphics, but maybe I just explain what these things are. These are actually two scenarios out of many others, but I just put here two. Basically, you can have a satellite that is in between the wireless base station and the mobile device. So that's what we call a transparent satellite. The satellite will take the signal from the base station, which is on Earth, and you basically transmit it up into the sky and then beam it down to the user. And that is a transparent satellite. On the other hand, you can put the entire base station in space. And that is what we call a regenerative satellite. Now, there are other models. For example, you can put part of the base station on Earth and part of it in the sky. And then, what part you put on Earth and what part you put in the sky, there are different pros and cons and technical, ways of doing it. But so that's one aspect. That's from an architectural level. From a physics, it's not very difficult to adapt the LTE and the 5G waveforms to work on LEO satellites. Even though the distance can be 500 kilometers or 1,000 kilometers, it's relatively can be compensated for. In 5G, the maximum distance, I believe, is 100 kilometers. But at the standard bodies, they're working to extend that to accommodate the 500 and so forth. So there are changes that you need to do to your timing and synchronization and cyclic prefixes in the waveform of the 5G and LTE. So I won't go into that detail. But what I want to say that it's not too complex. It is doable, and it's relatively straightforward. So this is not really a big technical challenge, and it will be done. The other trend that we see is the edge computing and the relationship or the business deals that are happening between the satellite companies and the cloud providers. So you have AWS, Microsoft, Azure, and Google being big players now in the satellite ground station, where they basically open up their data centers to host the antennas and host the ground stations for these satellites and use their fiber connectivity to connect between data centers. Just last week, I believe it was the most recent announcement was SpaceX with Google. There was also one between SpaceX and Azure. Of course, AWS was one of the first to open up their data centers to host ground stations. This is a big part of the enterprise moving to the cloud, the SD-WAN services. So you have to think about it more in terms of, the enterprise want to go straight to the cloud. Now, potentially you're undercutting telcos in part of the network because you're doing without them. It's not like telcos will be completely out, but the cloud players are substituting in some instances. And that's another key point. This is the CubeSats is another important one. CubeSats are, if I go back to the first slide, I mentioned about this. It's too many slides. You see like the Lacunas and the Keplers and the Fleet and the Kineis. All those guys are IoT constellations. What they're building is this kind of CubeSats. And the CubeSat is a standard that was started at the University of, Caltech or California Polytechnic State University, sorry, and Stanford University, mainly for research and for students to be able to do this, to launch satellites and study space. All like these units, they come stackable units, like in this kind of structure, 2U, 3U, 6U. So they're modular, and they include everything that you need to operate satellite, power, everything. So they're very small. You can see here down in the bottom, Lacuna LoRa satellite that is measuring 30 by 20 by 10 centimeters. So they're not very big. They're very small. They can launch them, they can launch many at one time. Um, uh, so even though the standard was set up in 99, now actually they're going through other revision, I believe 2018 version. The launch really picked up in 2013 with Planet and Spire. And here you see a picture of the mouth of the Suez Canal, and when it was blocked, and I don't know if you can tell, but these are all ships basically waiting to enter the canal, and that happened recently. The lifetime of these CubeSats is relatively short. It's 4 to 5 years, but I've seen that some were saying that their satellites can last 8 years. So it could potentially be more than the 4 to 5 years that I put here. And it's mainly used, these satellites, for Earth observation, remote sensing, and IoT M2M. So they're not used for communications or broadband. They're just not enough power. These things are actually, you can see they're low power and low power consumption. So these kind of satellites are actually, like leading to this kind of proliferation of LEO constellations. So not all of them are the type of 260 kilo SpaceX or the 500 kilo Telesat, things like that. Some are quite small. Another trend in terms of satellite and specifically LEO is the quantum key distribution. So one of the issues related to today, when we do encryption, we use the public key techniques. The problem with them is that some people think they can be broken, or potentially they can be broken either by computers getting very powerful or using quantum computers or something else, or there could be some other ways to break them, like algorithmically. But in any case, quantum key distribution, this is not futuristic thing. This is something that's happening today. The problem in doing quantum key distribution on Earth is that it's limited to 100 kilometers, or maybe longer if you use certain ways to amplify the signals. But without going too much into details, the range on Earth, if you do quantum key distribution, is very limited. But when you do it in space, now you can have satellite that will feed the keys to the two users who are communicating on Earth. And now you can extend the distance. And there was a recent Chinese trial that they managed to achieve 1,100 kilometers between two cities in China. And this is right now the record in terms of the distance for quantum key distribution. So this is an emerging area. It's a very important area. And we can see that LEO satellites in the future can be used or would be used for quantum key distribution for secure communications. Another trend is the geopolitical conflicts. So China, of course, has been on the rise. There's a lot in terms of, they're practically number 2 in terms of satellite launches behind the US. Also on the investment side, even though they lag the US quite a bit, but there's quite a, they're more than any other country aside from the US in terms of investment into space missions and satellites. They do plan their own constellations, so they have a number of constellations in the work, and this is all part of the geopolitical conflict that's happening today, whether it's related to telecom and many other industries. So I just wanted to highlight this because what this can lead to is that it can, like with LEO satellites, they're all about global coverage, right? And when you have different countries doing their own stuff, that can lead to fragmentation of the market, and eventually it's no good probably for anybody, but that's a fact of life, and this is something that's happening. So even the Europeans, they have plans for their own constellations, of course, and things like that. So there's that kind of national perspective. Well, OneWeb, like I mentioned, right, they were acquired by the British government. Finally, and to conclude, there is a need to have integration between the LEO satellite networks and all types of terrestrial networks. So that includes HAPS and private enterprise networks. This is work in progress. We had an initiative, myself and Riyad, my business partner, together with some partners at ESA and I2CAT to create a lab for interoperability testing. So and there are other organizations as well working on this. So just want to basically mention that this is another key part, that to integrate the LEO satellites within the terrestrial and other types of communication networks, GEO as well, and all these things. This slide is just I can send you the slide, but just shows what's now what's planned and what's in orbit. So you can see SpaceX is today #1 in terms of the satellite launched, 1,578 out of potentially 42,000. But I think most likely they will launch first the 4,400 and see how the business goes, and then work from there. #2 is the Chinese Guowang, or the national network, at almost 13,000 satellites, and then Amazon, and you go down the list. Kepler, actually, from Toronto, they do plan 140 satellites, and as I mentioned, they launched 15. Most recently, just a few months ago, or a few weeks ago, actually, on Soyuz, they got 2 more. So I think they launched like 9 in the last few months on the Soyuz rocket. And that's it. So I'll just open it up for questions. Here are some stock prices that show you can make actually money, but you just have to be careful about what you select. So the one that's doing well is Iridium, and the one that are losing is all the others. Intelsat, of course, went almost 0.
Thank you, Frank. If you want to ask a question, just unmute yourself and speak, or you can put something in the chat if you don't want to do that.
Okay.
All right.
Frank, it's Pat Doherty. Very, very interesting presentation. Thank you very much. Actually, I'm working on getting Telesat to do a presentation for us on their Lightspeed presentation in September. Okay. The question I have for you is, if we have multiple operators that are all looking at 4,000, 5,000, 10,000 plus constellations, what are the issues with electromagnetic and physical interference in the low Earth orbit?
Yeah, so this relates back to the spectrum rights and what they have, and they need to do coordination, right? So there is interference potentially between GEO and LEO, right? And it depends about the LEO, what kind of spectrum that they have. So they need to sort it out. And that's where regulators will have a play into this, right? So there's a lot of that will actually go on. And it is already today happening, right? In terms of, different conflicts and interference. There are priority rights and ways to handle this, but there's always, nitty gritty, the details that you have to go into, and you need to get involved, the involvement of the regulator sometimes to solve this. So this is a very tricky issue. Yes. And then as you have more and more constellations with these kind of spectrum rights, it will only increase in complexity.
All right.
So I hope I answered that. Yeah.
Yes. Frank?
Hi. Yeah.
Yeah, it's Josh Dorr from the Canadian Space Agency.
Yes. Hi, Josh.
Excellent presentation. Lots of information. Looking forward to having the deck. I was wondering if you could comment on 3 aspects. The first one is using HAPS or any other type of suborbital platforms. The second one would be the SATCOM for 5G. Well, actually, I could combine that with SATCOM for 5G. And what's the status in Canada? Where are we locating ourselves with international partners or competitions? Mm-hmm. And I think maybe I have to make a third question. I'm sorry, I'm not very clear. Is do we have a plan for some kind of a demonstration hub or center of expertise or something like that? So HAPS, satellite terrestrial integration in Canada, and maybe some kind of a 5G hub.
Yeah. So let me start with the SATCOM for 5G, right? Today, if you look, and I take it this is more from a Canadian perspective that you're referring to. So today, Kepler, I believe, is based on NB-IoT, and potentially they have a strong interest because of their technology to be integrated within that kind of network. Telesat solution will be very different. Now, this is an emerging field. If you really look at standards and the standard bodies, it's meant for release 17 at the earliest, which I believe will be in 2022. So there is still some way, because if it's finalized in 2022, you can expect products at least not earlier than, let's say, a year, probably, you know, after that, right? So let's say maybe 2023. So this stuff is part of the standard activities and the standard work. On related to the HAPS, I don't know, because with HAPS, it could be the HAPS basically could be communicating with the terrestrial network. So I don't know how exactly it will be, right? It is part of the 5G standards as well, but I don't know in terms of commercially what's happening. I know, for example, some Amazon or other big companies, right? They do have plans for this kind of solutions, right? For delivery and other things, but I don't know where they exactly stand, and especially technically where it stands, but it's obviously part of the standard activities as well. And the key point is to integrate them with the SATCOM for 5G. Now on the demo, I have to refer to you because I think you may be more clued in than I am. So on that one, I had mentioned that you know, we were trying to do something in Europe, right, with I2CAT and ESA, but maybe you can describe more on what, if you know, if you have more data on local, yeah, because my information on that is not as, you know, scant, yeah.
Yeah, well, on the what's going in Europe, they're slightly ahead of us. Luxembourg is very active in optical SATCOM, SATCOM for 5G. They have work plans, they have roadmaps, they have investments, they have ITTs, invitation to tenders. So they're very active. And I feel that in Canada, we're a bit behind. In fact, a lot behind. So I was just curious as to what activities you may know of that is actually being pursued in Canada.
Yeah, I'm not really aware of any, right?
Yeah, me either. When it comes to high altitude platform of any short term, I've been hearing about that for, I would say, decades. You know, high altitude, long endurance, high altitude pseudo satellites, whatever. And what do you think it's not taking off?
Okay. Yeah, I mean, just my perspective, right? So there are a number of issues. I think regulatory issues are some, among other things. But I just want to comment a little bit on what I have seen related to integrating the HAPS with the, let's say, the 5G networks. Okay, I don't think it's necessary to integrate them with the 5G network because if you look at the people from the telecom sector looking at HAPS. Today, they are architecting their systems to include interfaces where you can have controllers for the HAPS basically engage with the terrestrial network in order to change the characteristics of the antennas, right? So for example, because HAPS will be, let's say, flying over, I don't know, a few hundred meters, let's say above ground, right? The wireless network itself, the 5G network, 4G, all these networks, are not meant to communicate, you know, with things that are, you know, a few hundred meters above Earth. If you're in a skyscraper on the higher floors, you always will have problems getting reception, and you will see a lot of interference because most of the coverage and the power is focused towards the horizon, basically to hit the ground, right? Doing for objects in space, or not in space, but in let's say in air, right? Trying to track them with the terrestrial network, you're going to need to have, I believe, certain types of antennas. And that is in itself, I believe, is the complexity. That's why I'm not quite sure. I think that needs more thought and more study to see how the HAPS can integrate with the terrestrial networks, only from the perspective of the RF characteristics of the network and the interference environment that the HAPS will see. Right, so I think that is an issue. Today, I don't know. I don't think they're integrated, or if they're integrated, they're in a certain way that their critical function is not coupled tightly to the terrestrial networks. So that is, and that's the same argument, by the way, with the let's say the automotive sector, right? With the connected cars or the autonomous cars, is that do you need the 5G network to control the autonomous car, right? The connected car, or it should be pretty much independent, and you can only use the 5G network for certain things, because to count on the terrestrial networks, you need to have, let's say, edge computing, you need to have high reliability. What happens if your signal fades, and does that mean that you're going to get into an accident, or does that mean that this HAP is going to basically come down, or so there is that aspect. So these are like some of the thoughts that I have on this. But I mean, it's definitely an area of like some like Amazon and others are really looking very strongly into, right, for deliveries and different purposes.
I'm just curious because if you have a HAPS, you can have a regional service or capability without having to deploy hundreds of satellites, which is very costly. You can retrieve them, you can bring them down for upgrades and repairs. They're not as high, so latency is even better. The swap is not as high as you would need on a satellite. There's so many benefits, and yet it seems like there's such a reluctance. I was just wondering. Anyway, I can read on that.
I hear you.
Yeah. Well, thank you for your thoughts.
So Frank, I have a couple of questions for you. One is, what kind of operating centers do these systems have, and how they integrated with the terrestrial network operating centers? I mean, somehow or other you have to maintain and allocate resources for these systems. And my other question is on vulnerability to attack from like cybersecurity threats of that nature. Are these how would you view these systems from a security point of view?
All right. So the first one, I mean, they all basically they got their network operating centers with their operation support systems and even some their business support systems, right? But primarily their OSS to do this. Now, how they do it exactly, they have different options. Obviously, they need to have multiple redundant centers. Certain aspects of this control will be hosted in redundant data centers, right? And there is a whole different ways in which you can do it. Like, are you going to, for example, build your own system on your own cloud, your private cloud, or is it going to be something that's hosted in a public cloud? That is actually part of the services that the cloud players want to offer, right? And especially related to the ground station as a service, it's important, especially for people like the remote sensing and the imaging, because they don't necessarily need to have their own facilities, right, and their own ground stations, and they basically can leverage the cloud players. So that's the play that the cloud players are aiming for. So that's on how to do the in terms of the network management or support systems. On the security, on the other hand, so the new satellites are all basically, I mean, they're all packet based. Like if you look at, so basically we'll follow that kind of paradigm, right? And you need to have your security architecture. And that's a very critical part and very important part because, I mean, you don't want your satellites to be, controlled by someone else. So I mean, absolutely. But you basically, you have to develop your security architecture in a way that, you address these issues. And it's multiple layers, but it's a very, absolutely very critical part.
Thanks, Frank. Thank you.
Any other questions?
Thank you very much, Frank. I'm Shahzad, and it's all interesting. though I'm not expert in this field, but my question is with these LEO satellites or the low orbiting satellites, how far we are when our normal devices will be directly be able to efficiently connect and communicate, both upload and download? Just giving an example, imagine if we have a phone or any device at home, will it be a good idea? And when it will be feasible that these devices don't need local network, they just straight go to the satellite,
Yeah.
upload and download?
So if let me go to this because I show you like there are companies doing this today, or they plan to launch. They haven't launched yet, but there are at least three of them on this list: AST, Omnispace, and Link. These three companies actually are planning for your phone to go to the satellite directly. They're not there yet.
Okay.
They Link has 4 satellites in space. AST maybe one. Omnispace, I don't believe they have any yet. So they are still maybe 2 years at least, right, before they get that. But most importantly, the critical point about those constellations is that you need to coordinate because it's your so you're using your phone, which means that the spectrum, the frequencies are owned by that service provider that's serving you. Let's say it's O2 or Vodafone or whoever
Yeah.
your service provider is, right?
Mhm.
But that means that these companies have to have a deal with the Vodafone or O2 in order to serve you. And I believe, if I'm not mistaken, Vodafone has an agreement with AST. I believe AST, Rakuten in Japan invested, and I believe Vodafone also invested in AST. So because they need spectrum rights, right? They're going to use the same spectrum as the terrestrial operator spectrum so that your phone can work with that.
Interesting. If we take the even the phone out of the scope here, let's imagine we are going, just thinking of some example. Yeah, imagine if we have a farm or stock thing, and where we have to track some animals or plants or these kind of things. I mean, we don't want to connect to local network. Maybe we are at a place where the local network isn't available, and we put some small devices, and they can straight away connect to the LEO satellite. Even the we don't want efficient. Maybe they just once every 24 hour when the satellite is available, they just take something and upload something. I mean, how cost wise, are is it feasible? Is for a startup companies, can they think something like this? Can they go for such an adventure, or it's like making such device, not a phone, just a device which is
Yeah.
just send some signal, download, and for example, a plant is updating its status. Okay, I have this problem, or I need water, or I have something, so something like that.
Yeah. Yeah, no, you could. Definitely you could as a startup and all these companies here. So just to give you an example, Lacuna, which is a UK company, right? They're doing LoRa.
Okay.
And same with Fleet, but Fleet is Australian, and Kineis, which is a French, right? All three guys, these three companies are doing LoRa solutions. And I don't know right now what the LoRa module is, but I imagine it's few dollars, right? Or for the chip, and you can build a sensor, like you can build a transceiver, right, for a device, right, to track things with that. And this will leverage the terrestrial, the same as the terrestrial ecosystem, right? So it will work in the 900 megahertz, let's say, on license band, and you can leverage that ecosystem. Kepler, on the other hand, they're doing NB-IoT. Today, in China, the price of an NB-IoT chip is around $2 in volume. Okay, so
Okay.
it's more expensive in other places, but you see the price points are they're coming down they're coming down, and they're coming down fast, right? As these systems, because they're leveraging the same as the terrestrial ecosystem, the same as the terrestrial networks.
Perfect. That's good.
Yeah.
No, another question. Sorry if nobody, if there is no other question. Let
Yeah.
me take this opportunity. You mentioned that with LEO satellites, we have maximum user limits. I think you mentioned 20,000 or 30,000. And if the user limit exceeds, then we have to adjust antennas or maybe bring other satellites in there. And in that kind of situation, like there are so many companies launching their satellites, isn't there a governing body which can build up some standards that if in this kind of situation, imagine if there is a stadium, 80,000 people watching a match in one location, and they're trying to connect to one satellite. Of course, with 30,000 limits, it won't be possible. Then there should be a standard that every company has to follow or maybe implement. And this, in this kind of exceptional situations, these satellites from different companies should coordinate or support each other. Is it there or not yet?
So no, okay. So first of all, in terms of the capacity, this is more of a, it's related to the network. Let's say your service, capabilities, right? So you design, like, it depends on how much frequency you have, right?
Mhm.
And your throughput, and you do your calculations. So that can be a soft limit, but there is always a hard limit for the satellite, because the satellite can only be provisioned with a certain amount of memory and power and so forth, that it can handle a certain amount of users at any time. So there is a soft limit and there is a hard limit. But aside from that, this is more of an engineering aspect. In terms of the standard, there is no such standard to coordinate between them, but there are, but in terms of spectrum rights and orbital rights, that's where the ITU comes in play, and that's where the national regulators come in play. But it's not related to really in terms of like, hey, if somebody runs out of capacity, what will happen, right? I believe that maybe something in the future that can happen with coalition between these kind of service providers. I don't know, but we're far away from that point at this stage.
Okay. Thank you very much. Thanks for the presentation and for the answers.
Thank you. Yeah. Yeah. Any other questions?
It's
Yeah,
not a
just
question. Okay, so go ahead. I wanted to comment on the last question.
Yeah.
You got to think of the LEO system not as a satellite the way we used to do with GEOs, but as a as a complete system. So, for example, what Telesat is doing is they have beam hopping techniques, and they have satellite maneuvers, and when you have a hotspot like that stadium, we could pull in more frequency bands into that hotspot, which would provide you with more capacity on the satellite. The satellite isn't limited by the numbers of users per se. Theoretically, an unlimited number of users can connect. It is limited with the processing power, which is the throughput of the LEO satellite. So coordination between operators, that doesn't happen because we are competitors. But coordination within the system itself, that does work. And another comment previously to Frank. Frank, first of all, I'm impressed with your knowledge. Kudus.
Thank you.
Telesat also has the spectrum rights for Ka band and QV band. That's where they have the upper hand in Canada. And regarding what you were referring to in polar orbits, they also have around 80 satellites in their constellation and polar orbit, which specifically targets northern Canada and Russia for services like that. Just wanted to fill in
No, correct,
this gap.
correct.
Thank you.
You're absolutely right. No, thanks for that. And just to comment, I think I only put a fraction of the spectrum on this list here, and yeah, I
Yeah,
don't
so
think
it's
right. Telesat has a
it's
lot.
Sorry, it's
No, go ahead.
KAKU on the terminal side, and it's QV on the hub side.
Yeah, yeah. Telesat, I believe, has like 6 gigahertz of spectrum, if I'm not mistaken, or something like that. Some very big amount of spectrum. If I forgot what it is, but they have quite a bit. Yeah.
True. They got the spectrum earlier than Starlink. That's why they launched the second LEO prototype, which is just those spectrum rights.
Yeah. Thanks for that. Yeah. All right. Any other questions?
yeah, just a quick question, maybe. So you mentioned the capacity. I think it was like 20,000 users. So is that like Is that like per satellite or per constellation?
per satellite. So this is okay. Let me tell you how this number comes about. This number comes about from 20 gigabit per second. I'm trying to find it. It comes from 20 gigabit per second per satellite, based on 100 gigabit, 100 gigabyte per month plan, right? So you get around 20,000 users. Or you can dimension it for 100 megabit per second, and you get around 3,000 users. So I'm basically assuming, I think, around 3 or 3.3 bits per second per hertz, and then you do your math, and well, actually, you don't even need to go. You don't need to go to that, right? But because we already have the 20 gigabit per second per satellite. But if you do your capacity planning based on how much busy hour and how much traffic flows in a busy hour, right? And you work your way through it, these are the type of numbers that you get.
So for the entire constellation, for example, for Starlink, how many users you think it will support?
So you multiply that number by the number of satellites. That's how many users. But again, not all satellites will be utilized all the time. So you have to multiply it by the utilization number. So let's say they got, let's say they got 100 satellites, right? So at 20,000, that's 200,000 people. But then not all the satellites will be used because, there are satellites will be over water and there are no people there, right? So you multiply that, let's say, by 10%. So you'll get back to 20,000, yeah, for the whole constellation. I mean, just roughly, right?
So do you think that this is like a feasible business case? I mean,
yes, I think it is, because it is possible, because like some numbers that we ran, like 20 million, 30 million, again, it's all trade-offs, but it is possible to make a business. Like I've seen some projections from some investment banks, basically, looking at million, like, 50, like, sorry, more than 50, like, 100, 200 million people. But I don't think it's necessary to get that. I think you can achieve profitability with a lower number. And the problem is that it may take you longer, right? So you need to be well capitalized, but I think it's doable. It's doable. The 20 million or so, that won't give you very low terminal prices, because for terminals really to bring down the cost, you need to be in many tens of millions, right? Just like if you look at other like commodities, your cell phone or other things, you need hundreds of millions to commoditize that. So, but I think it's possible.
You mentioned that Starlink and Telesat, they have different business cases. Starlink is more user oriented, and Telesat is more like enterprise, kind of oriented. So which business case you think is like has a higher probability of surviving?
So they both have chances, but the enterprise, I believe, has a very good shot, because enterprises typically are willing to pay more, right? So you don't have that as much cost sensitivity, right, as the business case of the users.
Right, and I think Telesat needs like fewer satellites, so they have like lesser expenses, maybe.
Correct. Absolutely. Now it will still cost a few $1 billion, right? But and their satellites are longer. I believe they're like 10 years or 8 years. Let me see what they are. Yeah, like 10, like in their FCC filing, they had 10 years. So they are higher orbit. They are fewer satellites. They last longer, right? And they have the inter-satellite links to connect.
Right.
They can actually shift, just like it was mentioned earlier. Sorry, I didn't get the name of the other gentleman, but they can shift throughput to, like, they can allocate a lot of throughput to certain areas.
So they can like kind of steer their beams.
Yeah.
Right. I think I read somewhere that in terms of like in stock trading in stock markets, So
Yeah.
where they have high frequency, very high speed stock trading.
Yeah.
So they need like very quick connectivity between the stock exchanges, and they're
Correct.
going to provide or pay like one or maybe $100 million for 1 millisecond latency advantage.
Yeah.
Uh, so in that case, like I think Telesat might have a better business case.
Yeah. Yes. So that application like that, Telesat would be good for that. Now, I have seen some technical analysis published in scientific papers, like in terms of the latency. It really depends on how you route it, right, and how many hops you have, because every time you go from one satellite to another, you're incurring latency. So I think in general, I'll just give you like more of a qualitative, some analysis. In general, this will work over longer routes, only because in longer routes you may be able to. You're first of all not going over fiber, which is 2/3 the speed of light. Right now, you're going at the speed of light in space. So there's probably more advantage to go, let's say, New York, Sydney, for example, as opposed to New York, London. Okay, only because the distance is much longer. So and it really depends on how many satellites you're hopping over, and how they optimize that, right? So I don't know exactly in real life how it will be. I don't know if anybody knows at this stage, right? Maybe only the few people who are really working on it, but this is the way I would think about it. I would think the advantage will be over longer routes, and they really have to do good optimization so that these intersatellite links will basically optimize and minimize the path between the 2 points.
Right. Like we did some study, like a brief study, where we compared latency over satellite network, like for example, between New York and London, compared to latency over the terrestrial fiber network. And we found that even New York, London, over the satellite network, just considering the propagation delay, might be a better option.
Yeah, we've looked at that. Actually, we put a paper out on submarines because we looked at that. But I don't remember the detail in terms of like, okay, what area, like at what certain range you will break even, right?
Yeah, for Starlink, I think what we found out that we were like analyzing this kind of situation, and we were considering Starlink phase 1, where they have like 1584 satellites. So we like found out that if you are at 550-kilometer altitude and the terrestrial distance is more than 3,000 kilometers, so above that distance, if you go over the satellite network, that will give you a better latency as compared to the terrestrial fiber optic network. And the longer the distance, like for example, if you go from New York to Sydney, the better the latency offered by the satellite network as compared to the terrestrial fiber optic network.
So the unknowns usually in this is the latency that it will be within the satellite, right? Because
yeah, I'm just talking about the propagation delay.
Yeah. But the key point here, the unknown, it will be two things. Will be one, the latency within the satellite, and number two will be the route, right? Because these satellites are moving, so you need to update the routing, and that's actually a technical challenge in terms of these satellites, because the router is in space, but they're continually moving, so you need to update your routing tables and everything, right? Because when you want to go from point A and B on Earth, but you have all these satellites are moving in space, that's a key challenge that you have. And how they do the routing to minimize the path, and and how many satellite hops you need to hop over, right? That is going to be, that will depend on how they architect it, and that's what I don't know. I don't know what ultimately will be deployed.
No, that's very true. Actually, in another study, we considered the hop delay or the satellite delay, mainly the processing delay.
Yeah.
Where we are saying that so this processing delay is mainly based on the fact that when the packet comes in, the satellite or the node has to examine the packet header to make the correct routing and switching decisions. So when you add the hop delay, So the longer the connection, for example, between New York and Sydney, so the more the number of hops, and the more the no delay, and then things look different as compared to just the propagation delay.
Yeah. So that's an interesting question. There's quite a bit. Well, I have seen. Okay, I shouldn't say quite a bit. I have seen one paper, right? But I'm sure there are more. Yeah. And what's your company name, by the way?
Yeah, so my name is Aizaz Chaudhary. I'm basically in academic environment. So I'm a research associate at Carleton University.
Oh, cool. Okay, nice. Maybe we can connect on these things later. Yeah.
Sure, definitely. I'd love to.
Yeah.
Thanks. Thank you so much.
Oh, thank you. All right. Any other questions?
Frank, this is Bill Smythe. You said that this will eventually become a viable business option. How much will it impact the telephone companies, and when should I sell my shares?
So, okay, I don't think it will impact much the telephone companies. I think it's complementary rather than competitive. So I wouldn't advocate selling any shares. Number two, just to go back, there are many constellations being planned, and it's not necessary that all of them will be successful, and many of them will likely fail as well. So many people say only 2 or 3 will succeed. We'll see. I don't know, but yeah, I mean that's what I think will happen. That many will fail, few will stay, because again, like I don't know if you can they see the key question is how many users will be out there, and that's a big question that nobody really knows. Today, between Hughes and Viasat, you have around 2 million subscribers, and that's in the United States, and that's the biggest market in the world. So the question is, how many more subscribers can you win? And that's why when I talk about the geopolitical fragmentation, because you need to have access to a global user base so that you can load up your satellites. And if you don't have that, if different countries are fighting, then there is less or fewer pool of users eventually, right? And that's going to jeopardize the business case for these constellations. So yeah.
Thank you.
Yeah, you're welcome.
Frank, I've just got a quick question. If one of these companies does fail, what are there plans in place then for the control of the satellites after, say, a company's got thousands of satellites in the air and they go out of business? What happens to the control of those? Is there a sort of regulations around that, or?
So okay, I think they're all required basically to deorbit. I believe that's part of the process, right? In terms of deorbiting these satellites in a way that it doesn't lead they have responsibilities, and I believe they designed them in a way that they can deorbit them, and the majority of these parts will burn. And I believe there are certain amount that cannot burn and things like that. I think there are rules on these things. Yeah. But what happens? That's a good question. I think there has somebody who will need to basically maintain this and address this problem. But exactly the mechanics, to be honest with you, I don't know. But that's a good question, and it is a very it's a major issue, right, in terms of space debris and what you do with them. Yeah, absolutely.
Yeah, that's a good question. Josh again from CSA.
Yeah, go ahead.
Similar thing happened with Iridium when they decided, not even a year and a half after reaching FOC, full operating capability, they threatened to shut down the satellites and deorbit them all. And luckily for all of us, I think his name is Dan Colosi. He bought the constellation at a fire sale price, and it survived mostly from a big check from the U.S. military, because the U.S. military did not and still don't have a constellation that can provide direct satellite connectivity to a handheld. So for, through soldiers on the move, they really needed that capability. So my guess is that if any of those constellations was to bite the dust, yes, the plan will be to deorbit them, but my guess is that somebody would buy them first to see if they can give it a go. Because there's billions of dollars being invested, and if you're going to have thousands of satellites with all the infrastructure, I think it'd be a shame to let it go.
Correct. And that's what happened already with OneWeb, the last one, right? They
Correct.
spent $2-3 billion, and they had, I don't know, 76 satellites last year.
Yeah.
And the British government ended up buying them and resurrecting them, and now they're out again raising funds, and they have 182 here on the table.
Correct. So there's always reasons. Either sometimes it's political, sometimes it's just to for the UK government, as you know, when they were kicked out of the Galileo program as the result of Brexit, they didn't want to be the second cousins to their European counterparts. So they said, you know what? We got at one point they were considering building their own Galileo GNSS, a UK GNSS, and then they realized it's very expensive. So I think OneWeb could even over time provide the PNT, positioning, navigation, and timing capability in addition to SATCOM. So, people always find innovative ways to use what other people leave behind, and they may have to restructure, repurpose, refinance, but I doubt very much that a very large constellation would be let go to deorbit and to never see any use.
Yeah.
Okay, thanks.
A quick question here. What do you think that you have a slide that show the different networks that LEO will interface to? I'm just wondering what your thoughts about the top 2, top 3 networks that you think LEO will interface to, and the most important networks that LEO will interface to. Thanks.
This one? This slide? Or
Yeah, I think there is a slide that show a list of all the different networks that
this one, the
LEO
last
will
one.
interface. Yeah, so what are your thoughts? Like, which one do you think which network do you think will be most important to that will interface with you?
Yeah. So today you have the mobile 4G, 5G that's already being in the process of being standardized, right? You have the cloud and CDN data centers. So you already saw that Azure and Google, right? They're hosting ground stations. So there is direct to the data center and edge computing. So that is again happening today. There are constellations with IoT and low power wide area networks like the LoRa and the NB-IoT. So that is happening also today. It is fixed wireless access, but again, I would maybe characterize that or put that together with the mobile 4G, 5G, because there is fixed 5G as well. So that can also be part of that. Geo is again, let's say with Eutelsat like invested. Now, I don't know exactly, like today they're separate networks, but potentially at some point in the future, especially when you look at, let's say, US Army or military, they have those kind of visions or plans, I guess, about, GEO, LEO kind of integration. So HAPS, I think, is more, we talked about that, I think more longer term, only because it's an emerging technology. Private networks, that can have like elements in the 4G, 5G again, but that's basically enterprises integrating their terrestrial networks and wireless terrestrial networks, right, with the satellites. So there is a business element to that. I don't think it's as much a technology element, but just to make the business case. So these things are happening. They're happening. They're happening, and then they're happening at different layers. So, for example, when we talk about LEO integration with 4G, 5G, we're talking about the physical layer. using the RF, the same physical layer. But if you look at constellations like, for example, Telesat, complete and MEF, Metro Ethernet Forum compliance, that kind of integration on the IP side as well is happening, right? So this is in progress, but it needs more like, I think, firming up and focus, and just to enable like the entire ecosystem, right, to mature.
Thanks.
Yeah.
Okay.
Like,
I think that's.
sorry, go ahead.
I think. No. Go ahead. I'm just going to wrap up in a minute.
No, I was just going to say, like,
Frank,
Yogi Berra used to say that it's difficult to make prediction when it's about the future.
Yeah.
Remember when Bill Gates said that there's nobody will ever need more than a 486 computer?
Yeah.
So
you never know.
Okay.
No, but one of the things, I mean, it's far-fetched, but with the pandemic, one of the things the pandemic showed is with people working from home and, virtual meetings, I think that for that, or for entertainment purposes, we will be pushing for things like holographic traffic and imaging and videos, and so that you can actually feel as if you are literally sitting with your colleagues in the same room in a 3D world. That would require tremendous bandwidth and very short latency. I mean, it's not as far as we think. Sorry.
No, it's okay. I thought maybe that's a good point to wrap up, because it is amazing how things are moving on, and it'll be really interesting to see how all this area evolves. Frank, thank you very much for the really informative presentation. I'm sure people can reach out to you if they've got more questions.
Absolutely. So I'll share. I can share the deck, and I have my contacts on the last page. So
that'd be great.
That's great. David as well. Thank you for organising it, and the other Frank Johnson. If you're there somewhere, thanks for hosting this session for us. I think our next session's in June, isn't it, David?
Yeah, we're trying to do June 24th, and that will be artificial intelligence, machine learning, and how can it handle fraud.
Okay.
June the 24th, yeah.
Okay, and thank you all for coming. I know some of you have left already, but thanks for coming, and thanks for being with us this evening.